heavy gases generally want to go down. So those types of forces with momentum, all of this will impact how my material gets dispersed. So it's not an easy task to model a system that considers all of these. And so please note that it's not an easy thing, and the equations we have are basically an approximation. They will never be an actual assessment. Nowadays, with technology, we have the beauty of having sensors and online monitoring systems, and you can use drones. So in case of a release, you can release a drone to automatically track and try to collect data related to the concentrations of a release. But we don't wait for the accident to actually get the concentration, right? We actually want to predict what will happen on scenarios that we are considering of what can go wrong to prepare for it, right? To make sure we have the right emergency response team in place, we have the right evacuation drills. We know if that material is going to cause this much impact, then maybe more safeguards and protection might be needed to be added. Any questions so far, guys? All right. Now, the wind speed, how it impacts. Well, as the wind speed increases, then the plume becomes longer and it becomes narrower during a continuous release. And also, as the wind speed increases, the concentration or the maximum concentration of the toxic material gets diluted. So this is the impact of wind speed. I want to again emphasize that the highest concentration you will experience will always be at the point of release, where the release is, right? But what we are interested on in using dispersion modeling is what's the concentration, highest concentration downwind near the ground, where people might be, right? And this is what the models help us to predict. That concentration will always be less than the original one, but the highest concentration has to be estimated at some distance downwind from where the release occurs. Now we said atmospheric stability is also another parameter, right? Is this related to this? Your phone? Can you put it down, please? All right. Atmospheric stability has a big impact. We just said that the lighter gases want to go up, right? And the heavier gases want to stay on the ground. Now, what parameters impact the density of gases? Molecular weight. Okay. If I have the same gas, what other parameters impact its density? Temperature, right? And so this is where the atmosphere comes into place. And our temperatures during the day are completely different than our temperatures during the nighttime. During the daytime, we notice that the closer we get to the ground, the higher the temperatures are on the ground. And the reason for that is that on a very clear day, especially in Qatar, the sun radiation hits the ground and causes a lot of insolation. This is where a lot of heat is going to be absorbed on the ground as a result of radiation. And because of that, we find that the temperature difference between the ground and the atmosphere becomes much, much larger during the daytime, right? At nighttime, what happens? The temperatures near the ground are a lot more cooler than the temperatures in the atmosphere. So the opposite happens. During the day, temperatures on the ground are much higher than if you go up. At nighttime, the temperatures near the ground are a little bit cooler than the air that would be on higher levels. And because of this, if I have a release occurring during the daytime, what? The lighter gases are going to be where? How are they going to sit down? The lighter gases will be near the ground because the higher temperature is the ground, where the heavier gases are on the top. Is that normal? No, it's the opposite. So what do gases want to do? The lighter gases are going to want to go up. And this change in buoyancy force is going to cause mechanical turbulence in the atmosphere, making the atmosphere unstable. Okay, so the stability of the atmosphere is impacted greatly by the temperatures on the ground. And the temperature on the ground depends on the time of day, but also depend on, is it a clear day? Do we have some clouds? Is it a stormy day? Why?
Temperature also.
Exactly. If you have clouds, the temperature is going to be a little bit cooler. Less impact of the insolation due to radiation is going to be felt. And therefore, you'll find that the temperature gradient between the atmosphere and the ground is going to be smaller, causing less turbulence, which making that atmosphere a little bit more stable. So, this has a huge impact on the stability. Now, during a release, do we want to have a stable atmosphere, or do we want to have an unstable atmosphere to reduce the impact on people?
Stable.
Okay, so if we go for stable, it means the heavier gases are going to stay in the ground, the lighter gases are on the top. And where are you located? Do you live up in the atmosphere, or do you live on the ground?
Ground stable.
So if you're on the ground, you're going to feel the highest impact of the concentration of the released material. That's not what we want, right? We want, or we can't design the atmosphere, but the more suited atmosphere during an accident would be the one where you have high wind speed or you have a very highly unstable atmosphere so that you can take advantage of the mixing that will occur and the dilution of the concentration of the material. So this is important for you to understand. All right. When we classify the stability of the atmosphere, there are three major categories. We have unstable, neutrally stable, and stable. And then those are further broken down into 6 classes when we're looking at dispersion modeling. Let's take a look at the first 3 major categories. In the first one, the unstable one, we said is because the air with the lower density is near the ground and the air with the heavier density is above the ground. And this is usually when you have very high presence of thermal radiation and you feel the insulation changes. And because of that, you start to feel a very highly turbulent atmosphere and very unstable. So here, buoyancy forces are helping to cause mechanical turbulence. The second category, the neutrally stable one, is the air above the ground is warm, but the wind speed is high enough that it's what? Helping to cool off that air. And because of that, we're reducing the effect of the actual thermal insulation that's happening. And so you have a little bit neutrally stable conditions, which means that you're neither, mixing or it's neither highly stable. The stable one, this is where heavy gases are on the ground, light gases on the top, limited impact of buoyancy forces, and therefore the temperatures on the ground are low enough to help make that happen. And during this kind of conditions, we have a stable atmosphere, and the highest concentration of gases will be near the ground. When we divide them up into 6, the first 3, A, B, and C, are the unstable conditions. Extremely unstable is A, B is moderately unstable, and C is slightly unstable. The neutral stability is D, and then E and F are the stable classes. We have guidelines that we use to help us determine what class of stability we have, because we need it to be able to do our modeling. And so they're based on wind speed, time of day, and the cloud coverage. And by the way, these are not etched in stone. They're not exact. They're more, let's say, fuzzy types of guidelines in terms of the stability of the class. So these 3 columns here are all talking about daytime, and the last 2 here are talking about nighttime stability. We said A is the highest unstable, and F is the highest stability, right? Notice what classes do we have at nighttime?
D.
D and F, mostly stable. Why?
Because the ground temperature.
Because the ground temperature is lower, the heavier gases are on the bottom, we don't have much turbulence, right? So it's going to be mostly stable at nighttime. During the daytime, we have the more unstable classes, A through maybe up to D. And it depends on the wind speed, and it depends also on, do I have strong insulation? This is where you feel the radiative heat on the ground, or you have moderate, where you might have some partial coverage, or slight insulation. And this is when you have a storm where you don't feel the impact of this radiation. Now we'll see how daytime is impacted with speed. If you have very low wind speed, right?
Yes.
No clouds in the atmosphere, perfectly clear day. This is the
Turbulent.
perfect conditions to have the highest instability atmospheric conditions. Yeah? As the wind speed increases, what happens to the stability?
Decrease.
It becomes more and more stable. It increases. Stability increases with wind speed. Why? Because you're helping to lower that temperature gradient that you're feeling as a result of the wind speed, and therefore helping to reduce the turbulence. Okay? So even though wind is causing turbulence, the turbulence due to the buoyancy and forces is not going to be as high. And so you'll have more stable atmosphere as the wind speed increases. With moderate insulation, again, the stability becomes a little bit more stable because you have some partial cloud coverage, and you'll see that with more, like a stormy day, the cloud coverage is going to be higher, and you'll see that the impact is felt on the stability of the class. At nighttime, look at the impact of wind speed. If it's low wind speed, everybody's happy, things are cool, they're where they're supposed to be. But as soon as wind starts to come in, what is it doing? It's going to start moving the heavier gases a little bit to the top and the lighter gases to the bottom, starting to cause a little bit of motion. And this motion is going to result in a little bit more instability. Not stability, instability, right? Causing it to be more unstable, going from class F to a class D, which is neutrally stable. Okay? Be able to understand these relationships because you have to describe the system that you're trying to model later on.
Also, Doctor, which of the scenarios are considered the most that we can manage to contain the leak?
So it's a good question to ask, but let's rephrase it a little bit. What condition helped to reduce the impact of the accident on the people and the environment? So the ones that have the highest instability, category A, B, will be the ones to reduce the impact on the concentration downwind. Okay? And then that depends on if it's daytime or nighttime. Right? Usually higher speeds are better at nighttime. Lower speeds are best during the daytime so that we can have a little bit of turbulence, right?
Yeah.
At some point in time, the impact of wind takes over the impact of the mechanical buoyancy forces, depending on the wind speed.
Yeah.
Okay. So, atmospheric dispersion is a function of wind speed? Absolutely.
Atmospheric stability.
Absolutely.
And buoyancy.
Roughness, the height of the release, absolutely, and momentum and buoyancy. We saw that, right? And we'll take a look at a bit more at the roughness and the height release impact on how gases get carried away. If I have an unstable atmospheric condition, does the effect of buoyancy enhance the mechanical turbulence? Yes or no? True? Why?
Because
The heavy and light clouds will be mixed.
Yeah, but what causes it?
when
During an unstable
The
atmospheric condition.
increase of the temperature.
Exactly. The bigger temperature gradient between the atmosphere and the ground, because of that temperature difference, this is where you start feeling the buoyancy forces taking over, right? All right. Let's take a look at the impact of release height. So, as the stack height increases, so this is a stack. Could be a stack where you have vent gases being sent to flare, and then the gases are being released from the top. As the stack height increases, the distance downwind that the plume touches the ground starts to what? Increases, right? The higher the release point, you will feel the impact of that plume a little bit further down. If my release height was down here, I would feel the plume hit the ground here, right? The higher I go up, the longer it takes for the plume to reach the ground. So this is a fact. And the further downwind the plume gets carried, it means the longer it is, the larger the area that gets impacted by the release. But keep in mind that regardless of the wind speed, the total amount of material being released will be exactly the same. How it gets dispersed depends on the height of release and the wind speed, right? What is the total amount of material being released? I can estimate it using source models, right? Our source models help us to determine either the amount or the rate of the material released. Now, when we start to look at these models, the models depend on the type of gas and the buoyancy of that gas, right? And buoyancy depends on the molecular weight, and it depends on the density of the gas as it compares to the density of the air, right? Because where the gas is going to be released. So if I have a gas that's heavier than air, right? Anything with a molecular weight more than 28 point something or 29, initially, once it gets released, what's going to happen? Initially, it will hit the ground, and then it will bounce, and it will start to mix with the air to the point where it becomes neutrally buoyant, right? It's mixed with the air, it's suspended in there. If I have a gas that's light during the release, right after the release, it's not going to hit the ground. It's going to be quickly buoyant into the atmosphere and will reach neutrality much, much more quicker. What type of gas I have and the density of that gas is going to impact the way in which it's going to get dispersed. This is the point here. So gases that are lighter than air will follow this kind of path. Gases that are heavier than air, which are most hydrocarbons, heavy hydrocarbons are going to be heavier than air, then they will follow this kind of path. Eventually, at some point in time, they all become neutrally buoyant, and this is what our models are based on. They're called neutrally buoyant dispersion models, okay? Now, the models we use to estimate, as I mentioned, these concentrations downwind are based on this neutrality of buoyancy. And there are two models. One's to model puff releases, like the one you're seeing here. And we said a puff is when you have a lot of material being released all at once. You have a big plume, and then that plume gets carried away downwind. Or we have also neutrally buoyant models to model plume releases, where you have continuous release of material as a result of a leak or some kind of relief activity. Both can be modeled. Now, having those two types of models, we also need to clarify. These models are not perfect, and real systems are not going to be easily modeled either as plume or as puff. They might be somewhere in between, but it's an approximation that we use. So how well you define your system and which model you select will help you to be closer to what's happening in the real world. Typically, the concentrations we're measuring for these gases is going to be in parts per million, right? Another factor we said that affects the way gases get dispersed has to do with the surface roughness. And surface roughness is that if your facility is near a city, an urban city, then the models are going to struggle in predicting because we don't have many models that can do that. But models also consider if you have vegetation, usually, for example, Masaid. It's desert, right? So we can consider it's that similar kind of vegetation in our models, and our models are able to predict a little bit better in those types of environments. Notice that sometimes vegetation might be a little bit hilly, so you have terrains, things that are moving up and down, maybe similar also to Masaid, where we have sand dunes that might impact the direction and the way in which the materials get released. So these models that we are looking at really have limited space to account for the surface roughness, although it asks you, is it going to be a rough surface? Is it near an urban release, or is it going to be a rural release, meaning somewhere out, like in Masaid or Ras Laffan that we have. So quickly, give me the 4 or 5 parameters that we said impact dispersion. Buoyancy.
Atmospheric stability.
Atmospheric stability.
Wind
What's the third one?
Wind speed.
Wind speed.
height.
That's in atmospheric stability,
Oh,
temperature.
The height.
The height of release, very important.
When
What else?
the roughness.
Roughness, surface roughness. Excuse my writing. It seems the older I'm getting, the worse my handwriting is becoming. I'm starting to scribble, and you don't have the interest to finish words for some reason in writings nowadays. All right. I wanted to give you a pitch here. If you're interested in safety, this is the time maybe where you can start this course on ELA. If you have time during aid break. And before that, you should have maybe looked at the source model lecture, which I also kind of highlighted. It's made up of 3 major units. It covers mostly what we are covering in this class, but it goes a little bit deeper in terms of regulations and what the industry is looking for. Now, the models we're looking at, when you're trying to model dispersion, you have 2 approaches. One of them, you do full mathematical modeling of the system. And this is where you're considering the eddy diffusivities, you're looking at mass transfer coefficient, which is a function of many parameters, and you have a very nice, what we call theoretical model to help us predict the concentration. Now, the issue with this is finding the mass transfer coefficient that represents the system is not really possible easily, and it's not easily measured experimentally. Okay? The other approach, which is what we use in the buoyancy models that we have, is we use dispersion coefficients, which can be experimentally measured. And this helps us to determine what is the expected standard deviation of my concentration profile. And so you'll find the dispersion models we're looking at are going to include dispersion coefficients that are a function of the space where we are in the X, Y, and Z space. So because of that, let's take a look at our coordinate system. So again, we have an XYZ coordinate system. 0, the origin is always at the ground below where the release occurs. So even if the release occurs anywhere after the stack, in the middle of the tank, whatever, the origin is always at point 0 below, right? Z is my height. So Z would be 0, X is the direction of the wind, and Y coordinate is in the crosswind direction. This is how we look at our coordinate system. X is always in the direction of where the wind is blowing. Now this is the form of the equation we have for neutrally buoyant dispersion for a plume. And this is the equation. You'll see that if we want to know the concentration at any location in space, is going to be a function of my release rate, Qm. It's going to be a function, obviously, of my dispersion coefficients. You'll see that there's dispersion coefficient for Z and Y. You don't see X in here because we assume that sigma X is always going to equal to sigma Y. Okay? By the way, this equation we rarely use as the entire equation. Usually we have a simpler form of the equation depending on the cases we're trying to estimate the concentration for. And we'll take a look at. But the full equation depends on the mass release rate. It depends on the dispersion coefficient, which take into consideration what? The stability, atmospheric stability, and they will take into consideration the wind speed. So you will see how when we estimate these coefficients, we have to know these, the distance downwind that we're interested in, the wind speed, as well as the stability class. The equation is a function of the velocity, and it's also a function of the height of release. So it's taking everything that we said that impacts my concentration, right? All right. For the dispersion coefficients, the sigma y and sigma z, we can extract it from these graphs, but we also have equations that can help us estimate these coefficients, and this is why we use them in these models. Now, the coefficients are a function of where am I interested to estimate the concentration? Am I 500 meters away from the release site? Am I 2 kilometers away from the release site? And it depends on the atmospheric stability. And if I know those two pieces of information, and then I can determine what is my sigma y and my sigma z. Please note that you have two figures for sigma y and sigma z. These ones are for what type of roughness? Rural release, right? This is where you're out somewhere, away from the city. And this could be the desert, you have grass next to you, you have vegetation. This would be the parameters for this type of roughness. We also have them if you have near cities. Again, to be able to get the coefficients, you need to know what location you're interested to estimate the concentration, and you need to know the stability. And within the stability, it's a function of velocity, isn't it? And solar insolation. If you don't have the graphs, you can actually just plug in for x, put in the location that you're interested in, downwind, and you should be able to, based on the class, get the right equation to help you estimate sigma y and sigma z. And notice that both of them have units of distance. Now, as I said, this whole equation we rarely use. We're usually interested to know what is the ground concentration, which means that at some point in time, in some distance x away, what is my ground concentration? And because it's the ground, z is going to be 0. And we plug into this equation. It's a function of my release height, my coefficients, my velocity, and my mass release rate. If I'm interested to know what is the concentration right below the point of release at the origin, then my height of release becomes 0. This term goes to 1, and the equation simplifies to this equation. Okay? So those might be two scenarios that we're interested in. We might be interested to know what is the maximum concentration downwind, right? In the plume. Because the plume, we know when it will hit the ground. But I'm not interested in the ground concentration. I want to know what is the maximum concentration within the plume. What did I say earlier about the maximum concentration?
Release point.
Always at the release point. But after the release, the maximum concentration downwind will be somewhere within the plume after it hits the ground, right? And to be able to estimate that, you don't know where x is going to be yet, because you want to know where is that highest concentration. So it requires a few steps. In the first step, you take your height of release and you use this equation to estimate your coefficient in the z direction. Now, once you know your coefficient in the z direction, you can come to your graph here, or to your equation, right? And the equation is a function of the distance downwind. You don't know what that distance is. But for this QZ, knowing the atmospheric condition, you can come down and determine where that is going to be. So the highest concentration downwind, the location of it, it's going to depend on the height of release. We use it to estimate what is that x. Once you know x, then you can estimate the other coefficients, sigma y and sigma x. And once you know that, then you can plug it into this equation here. And you can estimate what is the maximum concentration within the plume downwind from the release.
Professor, we should determine sigma x. Do we have sigma x?
Sigma x is equal to sigma y. So you get sigma z from this equation, you plug in here to find your x, the distance downwind where the highest concentration in the plume will be felt. You can then use it to get your sigma y and your sigma x, and you plug it into your equation here to be able to estimate what is the maximum concentration.
Doctor, this is only for the maximum, right?
This is for the maximum. Now, if you know the maximum, can you know the time it will take to reach the maximum? You know the velocity of the wind? You know the distance, right? Then the velocity times the distance is going to give you the time. All right. Now, those were models for plume release, continuous plume area. if we have an instantaneous release or a puff, first of all, notice something. When you have a puff release, initially at time t is equal to 0, this is the maximum concentration and the size of the plume. What happens as this plume gets carried away, this puff, sorry, the puff starts to get a little bit bigger because air starts to mix in with the gases that you have. So it makes the diameter of that puff a little bit bigger. But at some point in time, it gets a maximum size and then it starts to get smaller and smaller because the more mixing it has with the wind, the smaller the concentration within that puff is going to be seen. So the profile is usually small, it gets really big, and then it starts to go smaller. And if we take a look at the equation, the neutrally buoyant equation for puff release, it's a function not just of the coordinate system, but it's also a function of time. In continuous release, because the velocity is constant, right?
Yes.
No problem. But here it depends on what time you want to determine this concentration. So you have to include that as your input. Now, this equation or this model is a function again of the mass release rate. And this is not the release rate, it's the mass release amount. This is why it's Qm star. It's the total amount of material released at time t is equal to 0. And it's a function of the velocity. But where is the velocity? Do you see velocity in the equation? No, but obviously if you have a puff release, depending on the wind speed, that will impact the concentration within that puff. So the velocity, although it's not in the equation explicitly, it's embedded into the equation through the coefficients. Sigma z and sigma y depend on the atmospheric conditions and the velocity to be able to determine that. And we said, we assume that sigma s is equal to sigma y. If the wind speed is constant, then if I want to determine the time it will take to reach a concentration, I need to know what location am I interested in. I can determine how long it will take to get to that location, or if I know the time, I can determine what will be the concentration at a specific location. Okay, both ways it could work. And as I mentioned, the puff size starts to increase, and then it starts to decrease. When we're measuring the concentration for a puff release, we're always measuring the concentration on the ground below the center of the puff. Okay, so this is one of the assumptions. When we are looking at the concentration on the ground, it will always be, the maximum concentration will always be right below the center of the puff. Right? It will not be here or here. It will be right directly at where z is equal to 0 below the center of the point. Again, for the coefficients during puff release, we have equations. And you notice the equations are a function of x again. You can estimate it to estimate sigma y and sigma x, as well as for sigma z in units of distance. Or you can use the graphs. The graphs, again, you have graphs for rural release and you have graphs for urban releases. I only showed the other one, I think, for rural release. And these are my equations. Again, it can be simplified to the situation where I'm trying to estimate what is the ground concentration below the puff, right where the release happened. This would be the second scenario where the height of release is at the ground. Then the equation again simplifies to be this format. The main difference between this equation and the equation for the plume release is that you're using the total amount of material released and not the release rate, because it's the total material being released at time 0. Now, which models should you use? There are simple guidelines. If the situation you are describing has a release rate in terms of mass per time, then you use a plume. It makes sense, right? If you're given as the total amount of ammonia released from this incident was this much, you don't have any information about the time, then you can model it as a puff release. If the mass that is released over a period of time is equal to or less than 10 minutes, you again model it as a puff. You take a look at what is the total amount of material released within that short period of time, and then model it as a puff model. And one of the other assumptions we have is that most of the time the facilities are located in rural areas, so you should use the coefficients for rural modeling for vegetation. All right. Any questions so far, guys? Understand the concepts of how these models are developed? The types of releases we have, right? And the kind of information we can get. What does the EPA require when it's looking at companies reporting their risk management plan?
Worst case scenario.
Worst case scenario. So in the worst case scenario, they have to come up with a scenario that looks at maximum amount of material release or maximum release rate, and then model the impact that it will have on the environment and on people. All right. So let's take a look at this example here. We have that 10 kilograms per second of H2S is released 100 meter off the ground. So that's my height, right? Release height is equal to 100 meters. My QM is 10 kilograms per second of H2S. And we're asked to determine the concentration 1 kilometer downwind on the ground. So what is 1 kilometer equal to?
1,000.
Oh, 1 kilometer is 1,000 meters, but it represents by
Yes.
X. All right. We have to describe the
Atmosphere.
scenario. So it's a clear sunny day, 1 p.m. 1 p.m. means it's right in the middle of the afternoon. The highest degree of thermal insulation will be felt. And the wind speed is 3.5 meters per second. So I have my velocity, I have my mass rate, I have my height of release. What I'm missing is the atmospheric stability, right? All right. So if we go back to our table here, my speed is 3.5 meters per second. That's somewhere between here and here, right? And what kind of insulation do I have during the day? Strong
Strong.
or slight?
Strong.
Strong. So if it's between here and here, I have a category
B.
B, right? So stability class here will be B from the table. All right. And we are assuming rural conditions. Now, what should I be using? Plume models or puff models?
Plume model.
Obviously, because I'm given the rate, so we will assume plume release. So I need to go find my plume release equations. I need to get my coefficients. So let's go to figure 5.10. I can go there. So based on my stability class of B, what is my distance? 1 kilometer?
Yes.
So at 1 kilometer, I can come up here and I can read, no, I need to go one more, right? Up here to read my XY. And 1 kilometer here, I need to go to B to read my sigma Z. So this is around the 100 something, right?
Yes.
And this is the same, around the 100, this would be 10, so this is somewhere in here, 103, 104, right? Let's see how good my eyesight is. If it doesn't work, then you should use the equations, which are much, much easier. All right, so going to that, I'll get that my sigma Y, sigma Z are going to be 130 and 120 meters. And then I will plug in my equations for a plume model. And I'm interested in the concentration at 1 kilometer is for X. I have the mass release rate, I have sigma Y, I have sigma Z, the velocity is available, height of release is available. So I just plug in everything that I have, 10 for the release rate, 3.5 for the velocity, my parameters that I extracted from the graphs, and I will get that my concentration is 41.2 times 10 to the minus 6, right?
Yes.
And this is units of concentration, which I can convert to parts per million, knowing the temperature and pressure, atmospheric conditions. It equivalates around 29.7 parts per million. So if this material is released, and I go 1 kilometer downwind from the release site near the border maybe of the facility, I will know that the concentration is going to be 29.7. So that means within that 1 kilometer, the concentration is higher, most likely. And if I compare this with the TLV value for H2S, which is 10, I'm going to be overexposing, right? TLV is the formulated by the industrial hygienist. It's not the OSHA yet, right? If I want to know if I exceeded any limits regulatory-wise, I will need to look at the permissible exposure limit, the PEL, and compare. So obviously, I will have overexposure if somebody is near that 1 kilometer point. What are the units here, by the way? Kilogram per meter cube, the seconds cancel, right? Then I can convert it to parts per million using that equation.
Doctor,
Yes.
this thing gets me confused every time. Should it be the parts per million be milligram per liter, not meter cube?
The reason we say meter cube is for gas. In gases, we're looking at meter cube volume. If it was liquid, then we would be looking at liters, right? And in liquids, if you have liquid, the conversion between milligrams per liter to parts per million is going to be 1-to-1. It's easy to, we don't have to worry about the temperature and pressure effects because it's not impacting. But for gas, it has a huge impact. And the reason we look at cubic meters is because usually the concentration is in a 1 cubic meter volume space is what's being considered. Now, if we ask the question, where is the maximum concentration downwind? I want to know the location. Then I would follow this equation. Remember, we said it's a few steps. I need to determine where is the location first. So I first use this equation, plug in my height release rate, and find that sigma z is 70.7. If I go to table 5.2, I'll get that this is the equation for class B atmospheric condition for sigma z. I know what sigma z is. I plug it in here, and I solve for x, right? And I'll get that the location where the maximum concentration will be felt will be 590 meters away. And what do I expect? The concentration will be higher than the 29 that I calculated parts per million. So once I know x, I can plug in to my concentration equation. I can also get my sigma y parameter, plug in all of the values that I have, and I'll get that sigma y is 92 meters, and that my concentration is going to be 5.14 times 10 to the minus 4 kilograms per cubic meter, or 370 parts per million. So from the height of release, the highest concentration on the ground is going to be 590 meters away from the release site, and it's going to be a concentration of 370 parts per million. And that will be part of the, if that was your worst case scenario, this is part of the numbers that you will be reporting to EPA in your risk management plan. Another question I could be asking for this scenario is, what is the maximum discharge that will result in me being within the acceptable exposure limit of the 10 parts per million, according to TLV? So I just work the problem backwards, right? I know the concentration. And so the maximum will always occur in the same location. That's not going to change. But now my concentration is equal to 13.9 milligrams per cubic meter. I solve for how much should be my release rate, and that's very small. If you guys go back and remember source model, it's a very, very small rate, which is not really going to be realistic. So if any release happens, you will always result in overexposure in that scenario, and that means proper emergency response safeguards, PPE, and so on needs to be in place. All right. I think we can stop here. When we come back on Monday, we will take a look at another example for puff release, and then we'll take a look at some of the worst case scenarios that we should be considering in modeling using our dispersion models. And more importantly, we'll start to look at the other criteria, not just the permissible exposure limit from OSHA, but there's so many other criteria from regulatory bodies that we need to consider when we model these systems. Are we meeting the EPA's requirements? Are we meeting the Ministry of Defense requirements? And what are those endpoints called? And we'll see those, inshallah, on Monday. Monday, we do have a quiz on inherent safety lecture. So it's again a very short quiz, just to make sure you understand the four main principles, where it's being, you can apply it, can you always apply it, can you not apply it, those types of conceptual questions. Any comments? All right. Just want to finish off.